the Trellis track, and so we're going to spend the day talking about the leaf spine fabric, mostly, that we have built. That we've given the name, we just used to call it fabric, but now we call it Trellis. And to jump right in, the outline of my talk is going to be much like this. First, I'll talk a little bit about what is Trellis, okay, and why, what it actually entails. There's still a couple of seats, actually 3 seats up here, if you want to get it. And then I'll spend a fair bit of time actually talking about why Trellis, because when you look at it and the things that it does today, it's not obvious why somebody would want to do things this way as opposed to some of the other choices that are out there in the industry today, right, for fabrics. So I'm going to give my reasoning. I have come up with 4 things that I believe are important for what we are doing over here, and so I'll be happy to hear about feedback from you, what you think about that reasoning, and also feel free to interrupt me anytime you want for clarifications on the stuff that I'm talking about. If you have larger philosophical questions, I think those are better served towards the end of the presentation. I have quite a few slides, so I'll try to get through them as quickly as... No, go ahead, please, you can sit there, yeah, because I'm not going to use it for the next hour. So we'll go through that, and then briefly I'll cover the Trellis Roadmap towards the end. So I'll speak for about 45, this session is about 45 minutes, then we'll take a 15-minute break, and then we'll come back and hear from EdgeCore and Broadcom, who are our main partners in crime. And then after the lunch break, we'll hear some very exciting talks from a few other people who have recently gotten engaged with Trellis. So we have an exciting, and at the end of the day, there's a hands-on tutorial from Charles, who has done a lot of the development and design in Trellis. So exciting track. And hope we can keep you engaged and interested throughout the day. Okay, so to jump right in, what is Trellis? Okay. We call it a multi-purpose leaf spine fabric that is designed for NFV. Okay, and it takes open source software, white box hardware, okay, bare metal hardware, bare metal switching silicon, bare metal switching hardware built on merchant silicon. And most importantly, it's also based on SDN principles. Okay, so it's built on top of ONOS, and ONOS handles all the control and forwarding and configuration of the fabric. Okay, but 3 main principles: it's open source software, bare metal hardware, based on merchant silicon, and based on SDN principles. And the key word over here is that it's a multi-purpose leaf spine fabric, and I'll tell you what I mean by that. Okay. So here's a look at Trellis. Okay, so here's your typical leaf and spine fabric. Leaves here, spines over there, connected to racks of servers, of compute nodes. And the basic, and this whole thing is managed by an ONOS cluster. Okay, so what you see over there, this is the ONOS GUI. What you see over there are instances, multiple instances of ONOS that work in a cluster and together manage this fabric. So you can have 3 instances, 5 instances, 7 instances, whatever works in your particular deployment. Okay, so what are the features we support? First of all and foremost is we support access and trunk VLANs. So typically what we do is that the entire compute rack is in the same bridging domain. So traffic between nodes on this rack is bridged, and you can have access VLANs and trunk VLANs. Normally the things that you expect in bridging. Okay, you can have one subnet or multiple subnets. Subnets are the same as the VLANs in this particular case. The other thing that we do is once we start going from one rack to another rack, from one compute node in one rack to another compute node in another rack, that traffic then enters an IP network. Okay, so we support both IPv4 and IPv6, and internally we support MPLS segment routing. Now, that's not an external facing feature, but we do use MPLS labels when going from one rack to another rack. So basically, when traffic enters this particular leaf and it's destined to another leaf, we push an MPLS label, and the spines only forward on the basis of those MPLS labels. So there's no IP lookups that happen in the spines. Okay, and then on the basis of the label that designates that destination leaf, traffic is forwarded from the spines. Of course, all the spines have the same rules because traffic over here in a typical leaf spine fabric is hashed up to the spines. Okay, so some flows can go one way to that spine, another flow can go another way to another spine, but the rules in the spines are the same that are looking at the labels and forwarding the traffic. Why do we use labels? I'll tell you a perfect use case. We're working with a big service provider right now, and they are using hardware over here that could have as many as 100 or 200,000 IP rules. Okay? How many rules do you think they need in the spines? 10. Okay? So that's massive. Okay? Because now you have a separation of concerns between the rules that go in the spines and the rules that go in the leaves. And so when we have new routes to put in, we only update the leaves. We don't need to update the spines because the spines are simply forwarding on the basis of MPLS labels. Then that means that you can have very, very powerful spines, you know, a 32-port 100 gig device, say from Broadcom, which is a Tomahawk switch, or a 64-port 100 gig device, which is a Tomahawk 2 chip, or a Barefoot Tufino chip. So very powerful, high switching bandwidth spines, but you know, only forwarding on the basis of a few rules. And over here, you could have very different switching silicon. You could have something like a Qumran chip from Broadcom, where the tables are larger, but the switching bandwidth is smaller. Okay, maybe 600, 700, 800 megabits per second instead of the 3.2 or 6.4 terabits per second over there. You could have a few hundred gigabits per second switching bandwidth over here, but a lot more capabilities, a lot more QoS capabilities, bigger tables, and so on, right? So that's the advantage of using MPLS and the difference between what we do in the leaves and what we do in the spines. We also support things like multicast, right? Both for IPv4 and IPv6. So if this is a multicast source and there are multicast sinks, the replication happens at two levels. So it happens in the spines as well as in the leaves to establish that multicast tree. And all of this is also programmed by the SDN controller. We also support layer 3, so DHCP relay. So compute nodes over here can go to a to a DHCP server in any place in this infrastructure. Now note that DHCP is basically L2, right? So so if you send broadcast traffic, it's not going to make its way through an IP network. So we established this. We use the controller to forward traffic for DHCP from the client to the server. So that's why we call it a layer 3 relay. And we do that for both DHCP v4 and DHCP v6. And finally, this entire infrastructure talks to the outside world using this functionality called vRouter. Okay? And we do this again for both v4 and v6. Now, vRouter is a dangerous term because whenever people think vRouter, they think that it's a router in a VM somewhere, right? It's a software router. That is not the case in Trellis, okay? In Trellis, this entire infrastructure, this whole infrastructure actually behaves as the router's data plane. Think of it as a distributed router, okay? The control plane that is the BGP traffic is in fact handled by the SDN controller, but the router's data plane is actually the entire hardware infrastructure. So it's the other meaning for virtual. It doesn't mean software router, it means a virtual router where the router functionality has been disaggregated, control plane is somewhere else, data plane is actual hardware. Okay, and I'll talk at length about that a little bit later. So again, Trellis is based on open source. It's bare metal switches and it's based on SDN. What we use today is hardware from EdgeCore, and you'll hear about that more in the EdgeCore talk. We actually, I'm showing one model, but we actually support 5 or 6 models from EdgeCore with different switching silicon inside it, Trident 2s, Tomahawks, as well as Qumrans. the thing is that it's the same software stack, whether it's inside a leaf or inside a spine. And this is the software stack we use. We start with software that comes from the Open Compute project, Open Network Linux, and ONI. Of course, there's Broadcom ASIC inside there, and that exposes an abstraction that is called OFDPA. That stands for OpenFlow Data Path Abstraction, on which we can put an OpenFlow Indigo agent, and that's the one that talks to the controller. Okay, so I'll give 2 minutes about why we use OFDPA. Okay, so early generations of OpenFlow-based switches, and you'll hear more about this from Joe's talk. Early generations of OpenFlow switches used to use this one table inside today's switching silicon, right? Merchant silicon that exists today. And clearly, this did not scale because this table, while very flexible, is limited in size, and you couldn't build production networks with such a small table. Well, what OpenFlow 1.3 does is that it gives you the ability to use all the tables that are there in today's switching silicon. And so the use of OpenFlow 1.3, on which OFDPA is based on, allows us to achieve this data plane scale, so you can build truly production networks with OFDPA. And again, you'll hear more about that from Joe's talk. So that was that was talking more about the data plane scale, but just as important in this, because Trellis is based on SDN and it's disaggregated, so we have to talk about the control plane redundancy as well. So you can imagine there are multiple instances of ONOS, and this is what happens. So a switch, I'll just leave that here so I'm aware of the time. All the switches in the infrastructure connect to multiple instances of ONOS. Okay? So in this particular case, you can see that the ONOS cluster has decided that this instance is going to be the master. And these other instances are going to be backups for that particular switch. Okay, so a different switch you can imagine that a different switch will have a different distribution, because again, it's the ONOS instances that have the responsibility of deciding mastership for any particular switch. So that particular instance has this one as the master, okay, and more. So now you can see that this distribution means that some instances could solely be backups, and other instances could be masters. And there are ways to balance mastership over multiple instances. So the thing is, spreading mastership over these controller instances contributes to the scale of the controllers themselves, scale of the solution with regards to the scale of the control plane. But the nice thing about ONOS, the great thing about ONOS is the same way that you do scale is the same way we handle redundancy as well. So imagine if 2 of these controller instances go down. Okay, so we lost a couple of instances, but we still have 3 instances up and running. So the things that happen when this happens is that, first of all, the remaining ONOS instances redistribute the mastership amongst themselves. So something that was formerly a backup, right, for that particular switch, now has become master for that particular switch, right? So we redistribute the mastership. The switches that have now lost connectivity to the instances that have gone away, they keep on retrying those lost connections. So once these instances come back up, they automatically reconnect to the controllers. And you can also have a watchdog, for example, that will bring back these instances, right? So the same way that we achieve scale is the same way that we achieve control plane redundancy. Okay? We've also worked a lot on data plane redundancy. So we have multiple links between spines and leaf switches, right? We also, this is one aspect that we haven't done yet, but we are working on that the access equipment, like when it's used in cord, you have multiple access peripherals, whether that's for residential cord or mobile cord and so on. The redundancy, we're still working on that part. We've just gotten this equipment up and running in one particular instance, but we have already achieved the redundancy of having top-of-rack switches, dual top-of-rack switches for the servers that are connected in the rack. We've also achieved redundancy to have multiple external routers, right? This is connecting to, say, metro router in a cord-based environment. So the ability to have these dual top-of-rack switches connect to multiple upstream routers and have these BGP sessions between them, that's also something that we have achieved, so this dual homing capability. Okay, so then how is this used? Okay, one, of course, Trellis, one big use of Trellis is in cord, of course, and when it's used in cord, there's actually, it's used in a slightly different way from what I've been talking about so far, in that the fabric itself is the underlay, and then in cord, there's also an overlay network, which is based on VXLAN, right? And the thing is, both the underlay and overlay are SDN controlled. So having this common SDN control over both underlay and overlay allows us to do a number of things, and work with XOS to do a number of things that are optimized just because we have this common SDN control over both the overlay and the underlay. Okay, and I'll talk about some of these things later in the presentation. So Trellis is, together with the underlay and the overlay, is the enabling network infrastructure for cord. That's one way to use it. Okay. So to give you another way to view the same thing, so here's XOS, which is the service orchestrator and infrastructure orchestrator, and then you have ONOS, and then you have a number of apps that run on top of ONOS, but it's the same ONOS that is controlling both the underlay network as well as the overlay network that is built out of virtual switches running in all the compute nodes and doing a VXLAN based overlay. Okay, so this is one way when it's used in cord, but there's also another way to use Trellis, right? So some of the service providers that we work with, they don't necessarily take all of cord, right? They already have, say, their own orchestrator, or they have different ideas for what they want to do in the compute nodes. Some actually don't even use an overlay network, but still they can use the underlay network to connect access equipment, the compute nodes, and the upstream routing equipment. So there is a use of Trellis in cord, the way we present it, the way we create the reference architecture, the reference implementation, and there is a use of Trellis outside of cord. So you will hear that throughout the presentation when we talk about the roadmap and so on. So hopefully now you have a good idea about what is Trellis. So I now wanted to spend some time to talk about why. Okay, now you have a good idea how we have built it. Here's the section where I would love to hear some feedback. I'm going to give you my opinions, and these are opinions, on why this matters. Why is it done this way, as opposed to some of the other ways. And I've come up with 4 reasons, so we'll go through them one by one. Okay. So I feel that Trellis is designed for service providers and NFV. Okay. And I want to take a little bit of time trying to explain that. Okay. So here is the use of Trellis in cord. I'm kind of showing a residential cord over here because here's a residential passive optical network connecting to also a white box OLT that we talked about yesterday in the R-cord track. But you can also imagine mobile customers and enterprise customers connecting to the cord infrastructure. Now, take a break and think about how the Web 2.0 companies build leaf-spine fabrics, right? So if you've read papers from Microsoft, from Facebook, from Google, you'll find that everybody uses a data center fabric that is a leaf-spine fabric. And how do they use it? Well, very simply, you could just turn on, you could buy a Cisco switch, for example, or a Juniper switch, right? And turn on the traditional networking protocols like OSPF and BGP, and that'll work, okay? Or you could go what the bare metal guys have done in the Web 2.0 companies where, let's say they get, number of ODM providers, EdgeCore, Quanta, and so on. You could buy equipment from them, and then you put your own protocol stack over there. Or you can do things in an SDN way. Google does things in an SDN way. Facebook and Microsoft actually have BGP implementations running in these boxes. So if you're using OSPF or you're using BGP, you'll still get a leaf-spine fabric, right? So why bother with Trellis? Because you could just buy bare metal stuff, and you can take a protocol stack and put it on it, and it'll work, okay? But the key aspect to remember over here is that when someone like Google, Microsoft, or Amazon, or Facebook do it, they have only one kind of traffic, right? It's IP traffic, right? So anything that is coming from outside over the internet is coming through IP, okay? All the apps that they are running in their data centers are all IP based, right? So they have optimized this to do just IP, and BGP will do that for you, or OSPF will do that for you. But that is not necessarily true when it comes to service providers, right? Because service providers have access equipment. This thing is not sending out IP traffic. I mean, it is IP, but it's predominantly double VLAN tag traffic. So who's handling double VLAN traffic over here if this is running with BGP, right? You have some other customers that are using even older DSL technology. That traffic is coming over PPPoE, okay? Who's handling that, okay? People over here are watching TV at home, okay? That's IP multicast. How many people are using IP multicast, right? Who's dealing with IP multicast over here, okay? So that's the point I'm trying to get to, that when you think about NFV and you think about service providers, they have to deal with a number of different types of consumers with different traffic types coming in, okay, that your normal BGP fabric is not going to be able to handle. So we need all these I remember talking to a service provider and said, welcome to the telco world. That's their life, right? That's their business. That's their reality. And so you have to have a fabric that has that capability to deal with all these different kinds of traffic coming in and service them. That's the first reason, okay? Second reason is SDN doesn't allow simpler, easier, and more optimized features. And there are actually many examples of this, but I'll give you one particular example because that's all I have time for. So remember we talked about vRouter, and vRouter being one of the features in Trellis, but not the normal way that you nearly think about vRouter, okay? So a physical router will have a data plane, it'll have a control plane based on traditional networking, it'll have some kind of management. But when you want to talk about vRouter, they'll say, okay, well, we'll take all of that and put that inside a VM. Okay, so I still have my data plane inside the VM, I still have my control plane inside it, and I've got the same kind of management software running that. And there are many, many examples of this basic vRouter functionality, whether it's called VCP, VBNG, VBRAS, you name it. Many examples of this in the industry. Well, the problem is that when you have an infrastructure that's running one of these virtual software routers, so to speak, to go to the outside world, you'll often have to hairpin through this. Okay, so that doesn't scale very well. It's well known. And you have to do this kind of hairpinning. Now you can scale it if you wish that, okay, fine, I'll keep the data plane inside the software router, the VM. I'll take the control plane out. That's a good step, okay? But even in this step now, you have to have something that is going to load balance through these boxes, right? But so you still have this hairpinning issue through this load balancer going to these data plane VMs. Take it one step further, and that is what Trellis does. Trellis already keeps the control plane out, okay? But the data plane, instead of having VMs that are having the router data plane, that data plane is now pushed out into the hardware, right? Where the entire leaf spine fabric essentially is the data plane of your router, okay? And we can do this because we have this SDN control over the underlay, but when you bring in the overlay as well, your router data plane has now extended to include these virtual switches as well. So this is how it works. We have Quagga or any other routing protocol suite running that is communicating with the outside world and establishing, say, the BGP session, okay? So the underlay control programs the leaf switches that are connected to the external routers to take this control plane traffic and send it to Quagga that establishes the sessions. And everything we learn from the upstream is then told to, so let's say, this vRouter app that is running on top of ONOS. That then tells the underlay that, hey, these are you know, if you want to get to these IPs, then you have to get to this particular switch. So the underlay control then basically programs the entire infrastructure to have your default route or any specific routes out of that particular box, right? So this is a distributed data plane for your virtual router. And in addition, the overlay control does the same thing to the virtual switches that are running in the compute nodes. So the net is that the Trellis vRouter is implemented as this big distributed router which presents the entire network infrastructure as a single router to the outside world. And the advantage is that no matter where your VM is in the infrastructure, it can go directly out to the outside world. It doesn't have to hairpin or go through a load balancer to go through some other infrastructure before it goes to the outside world, right? And this is key. And this is possible because in Trellis we have this common SDN control over both underlay and overlay. That's a big deal, okay? A lot of people have told us that this is a best-of-breed solution for this virtual routing problem that everyone encounters. So yes, so with Trellis, we can do there are other examples like this, multicast being another one, but the fact is that SDN does allow us to do these things in a more optimized way. The third new feature, the third reason why Trellis is that, yes, we are working with hardware now, but there's newer hardware coming that does allow you to create programmable pipelines, and I'll tell you what that means in a second, but it does give you that advantage that even new features can come in much faster. So the idea is, okay, today we may be using hardware where the features are fixed, because why? It's an ASIC, the pipelines are fixed, right? But there is newer hardware where you can reconfigure the pipeline. You can make it do new things, giving you the ability to create, to intercept newer kinds of traffic, to be able to recognize different bits in the header and do new functions to them, right? And that's what we are getting from P4 and the ability to configure a pipeline of your choice and then be able to program that pipeline using SDN, right? So like a number of, at least 2 service providers have told us that they would love to be able to terminate PPPoE traffic. Again, so in service provider world, different kinds of traffic coming from different types of their customers, and they have to be able to terminate those PPPoE sessions. Okay, not very easy to do when you have fixed functions or a fixed pipeline over here. You might have to do that PPPoE termination in software. Okay, but if you had the ability to reconfigure the pipeline to be able to recognize the PPPoE bits and terminate them in the hardware, well, that's very powerful, right? So, and you get this through SDN, you get this through P4 runtime. It's actually very hard to do. Now, if you think, if I was using traditional networking over here, traditional networking protocols running in each of these switches, okay, how do I now make my traditional networking protocols understand that I want to do PPPoE termination and then take the traffic and do something with it, and so on, right? But SDN gives you that ability. So we will have a talk later in the session from Carmelo, who is my colleague at ONF and is leading the work for doing P4 runtime and working with more programmable hardware. And finally, one more reason that I wanted to give for why Trellis is important as opposed to just using a traditional fabric with traditional networking is that it's completely open source. Okay, and this is something that I had difficulty understanding earlier. Okay, but here's my reasoning. These are all technical reasons. Everything that I've said so far are technical reasons. This is a business reason. Okay, so let me try and explain and see if you can grok that. Right. There are some service providers that we work with that truly want to own the code. Right. They truly want to be able to take the code and customize it for their needs. Okay. Now, you can imagine that somebody takes bare metal hardware from Quanta or from EdgeCore, and then the software stack is built by someone like Cumulus or SnapRoute. Okay. Now, if they want to customize that, they'll have to ask Cumulus or SnapRoute to build in the new features. right? And then who owns the license for it? Cumulus and Snapdragon, okay? But there are some service providers that we work with that truly want that features, those customization to be done in open source with the Apache license like us. So in the future, when they want to change it even more, they have the ability to do that without having to pay for licensing or a new feature from someone like Cumulus or Snapdragon. And the reason why they do that is actually kind of interesting. I didn't realize that when you buy a service from a service provider, it's branded for that service provider, but the service may actually be provided by a different service provider, right? So one service provider has actually is actually building that solution. It's actually providing that solution and supporting and managing that solution is just rebranded as another service provider's name, okay? So you think you're buying something from A, but actually B is doing everything for A. It's just rebranded as A. And that means that B, who is actually building everything, wants to have that kind of ownership over the code, over the ability to customize it, and then resell that to A. That's very powerful, okay? So that's one big reason for going with Trellis, which is based on ONOS. ONOS is open source, it's Apache license, and so on. So technical reasons and a business reason for why Trellis. Okay, so the last section of my talk is just to tell you a little bit about the Trellis roadmap, and here is where I want to bring out that distinction again. Yes, question.
So, question on OFDPA. So,
Yes.
my understanding is that OFDPA actually has to be developed into the NOS. Because you have a different SDK for each Broadcom chip, whether I'm Trident, Trident 2, or Tomahawk. So the NOS provider has to have OFDPA in there. Is there an open source availability for OFDPA for each chipset that we can pull into a NOS, or am I correct that we would have to develop that?
Okay, so Joe, you can take it, but let me just say 2 lines,
Okay.
right? So OFDPA does come from Broadcom. And it is not open source code. The API that OFDPA offers is open, so anyone can see the API, okay? But the code itself is not. You can have a relation like we do with Broadcom. You can sign their NDA, their SLA, and then you will have the open source code if you are interested in that. But Joe, I'll let you take it further.
Yeah, it's basically, basically that's the case. It's the same SDK for all the different chips. The hardware platform is going to be different as well. They all have different BSPs. Those are proprietary for like the particular hardware vendor. So essentially what you get is a built OFDPA binary that will run on that platform, and that you can use Open Network Linux to load. So it loads as a package.
So I can pull that in, put it in my NOS without any development and be running? Or
Correct.
are you saying
Correct.
there'd be development on our part?
Sorry?
Or are you saying there'd be development on our part?
There shouldn't be any development on your part unless there's some features that are missing or there's some special thing you need done. And that comes up all the time, in which case you either need a source license or you can get us to do it.
Right. Okay. But in principle, if you're happy with the features that are already included, then you can literally go on our website and download the OFDPA version that we are supporting. We'll give it to you as a binary, and then you can go and get a box from EdgeCore, load ONL on it, and then load that OFDPA version, and you're up and running.
Okay.
So we try to make it as smooth as possible for anyone if you're happy with the features.
The other question, which is not OFDPA related, in the picture you had before where you actually showed segment routing type ability,
Yes.
where are you actually pushing the labels on and popping them off? Because you'd have to have a max action. Somebody's got to hold IPv4 fib to do a match action and pop the labels on for the label stack to get through, right?
Right.
So where is that happening?
Typically, we are pushing the labels on the source leaf.
Okay.
Okay, and the labels represent destination leaf. It could also represent the path. We typically don't do that because default segment routing means using ECMP shortest path. So the ECMP shortest path is basically going to all the spines. The spines are where you're matching on the labels and popping them off and sending them to the destination leaf. So by the time it reaches the destination leaf, it's an IP packet again. There's no MPLS label, and again you hit the fib in the destination leaf to go to the particular server. So that's the default operation. Now there are other special operations that we do that I'll talk about in the roadmap where you're using multiple labels.
So potentially I could have a pretty big fib there because I have to not only deal with east-west within my data center, but east-west DCI to DCI, as well as peering. And if I am a tier 1 who has peering agreements and has to maintain peering agreements, I may have to do some balancing there, which means that I have to know each fib entry to be able to balance that out.
So, okay, when peering with upstream routers, we have the ability to do traffic engineering as well. So if you want certain routes to be going out of one of the top-of-rack switches and other routes to be going out of other top-of-rack switches, we have that ability to be able to distribute load over those two top-of-rack switches, and then the rest of the infrastructure also knows that to reach these particular routes, I need to reach one of the top-of-rack switches to go out of to a specific peering router, and the other one for others, right? Or you could just use default route everywhere, and then it'll be naturally load balanced to both of these, just through ECMP hashing, be able to go to any of the two top-of-rack switches and be going out. But the main thing is, it's the leaves that have the fit, the routing tables, and the spines are really just doing MPLS.
Okay. So one last one. Sorry, I'll try to make it my last. So what I've seen in the architecture pictures, you have your leaf spine, but off that you also have downstream, maybe customers connected into that leaf spine, right? And a tier 1 has an obligation to provide a default free zone, which at this point in time is like 600 and something thousand. And if I have to actually add redundancy to that, we can be well in the millions. Where in the architecture do you actually then provide a default free zone? I wouldn't think it would be within the leaf spine.
So I'm not aware of that requirement. No one's actually brought that up with us. And the numbers that you use, 600,000 or to a million, can you specify?
It's actually on the internet, so IPv4 routes are up to a 640 something
Okay,
thousand.
so the full routing table is never actually exposed to the central office, as far as I know. Everyone has pretty much said that the full routing table never goes down to the central office. And even the customer side, the access side, never has to see, because mostly it's just the default route that they care about, right? And they have specific, they might be, so for example, if you're trying to go to CNN.com, but you want to provide a caching service, you can intercept that traffic and send it to a cache as opposed to going out to the internet. But the entire central office is never actually exposed to the entire routing table. In fact, the numbers that we hear are on the thousands, not the hundreds of thousands.
So as a tier 1, going to a tier 2 or feeding to a tier 2, so a customer could be a tier 2 or a tier 3, I have an obligation to provide a default free zone with ads. And so I've actually been asked by a couple customers to provide that, and in FIB they want 3 million entries, and in RIB they want 10 million entries, which obviously no FIB can hold right now. So you'd have to cut that up. So the question I'm getting to, and maybe it doesn't apply to Trellis, but I would like to know where that actually happens. Doesn't have to be answered now. You just still have to have that to feed down to your tier 2s, tier 3s.
Right. So I think that's something that would happen not on the access side, but we have to come up with some solution on the part that is actually doing the peering, right? Whether it's with your tier 1 or with your tier 2s and so on. But again, I don't have an answer, a definitive answer, because we haven't come across that. Yes?
My question is shorter. Is the reason why the spine switches are not overlapped?
Are not?
There's no lag management between the spine switches.
So there's no connectivity between the spine switches at all, actually. The spines are not connected to each other. They're only connected to all of the leaves.
But you see
and that's yes, go ahead.
Other vendors, when they sell the SDN controllers, they have the dual lags.
No, but that's the thing. They don't sell leaf spine fabrics at that point. I think they tend to, I wonder if I can draw here, but leaves. Right? So if you look at traditional Cisco architecture, right? So you'll have top of rack switches, and they may be connected to each other. They're also connected to aggregation switches, and they are then further connected to, say, the routing data plane, right? This is the typical sort of 2x2 architecture that you get. But this is not a leaf-spine fabric. Okay? The leaf-spine fabric, you will have every one of these connected to all the others, right? And there is actually no need to be able to do this because the failover actually comes naturally. So if any one of these dies, right, the leaves adjust to remove that from the routing path and go through. This is where the multipathing benefits come in. There's never a need to actually go through from one spine to another spine to come down, right? So if you look at typical leaf spine architectures, you won't see these guys connected to each other, but you will see these connected to all the spines. Okay, so very quickly about the roadmap. I only have 3 minutes left before we take a break, but what you will find is that Trellis is used in CORD, and a few of these features like bridging and IPv4, unicast and multicast routing, and the vRouter functionality is actually used in CORD. But as I said, you can also use Trellis outside of CORD, and there we support a number of other features right now, like dual homing, IPv6. CORD is not IPv6 ready, but Trellis is. The DHCP relay, that's coming actually into CORD soon, and the ability to support pseudo wires, because in some cases, this is an IP routed network, but you have to take Ethernet traffic all the way from the customer to some other point. For example, in eCORD, the enterprise CORD case, you might actually want to go across multiple central offices completely on the Ethernet layer to support E-line services from carrier Ethernet. So that's where pseudo wires come in handy. So there are features that are not yet in CORD, but they are part of Trellis. Okay, and in the upcoming release in December, so dual homing has already been released, but there are some issues. So we have some fixes for it. That pseudo wire support is also going to come in. And we're going to try some initial QoS support. It's not going to be fancy, but we will have some of it over there. There's a lot of additional IPv6 features that have been contributed by our partners from Nokia and Infosys. That's coming in. And also, very excited, there's newer ASICs that are coming in. Cavium, you'll hear a talk today from Cavium, but they are Trellis ready. Qumran, I just mentioned it. We've been working hard with Broadcom to have Trellis ready on Qumran-based switches. That's coming in. We have another supplier other than EdgeCore. So we have Quanta on one particular Quanta platform right now, but more coming in the future. So there was a talk from Quanta yesterday about it. And we have started this exploration to have Trellis be supported using B4 and switches from Barefoot. This is not going to be in the 1.12 release, but I just wanted to bring that up because we have started that work. And there will be a talk from Carmelo, as I mentioned, later today. So lots of exciting talks today. So make sure that you, according to your interest, you do come and attend these talks. So we do everything in open. All our roadmap items are there. There are links to it on our wiki to tell you about what we have and what is coming. So just to summarize, my last slide really, what is Trellis? It's a multi-purpose leaf spine fabric. 3 main principles: bare metal hardware with merchant silicon open source software and SDN principles. When you use it in CORD, Trellis is not just the underlay, but the overlay as well, together under SDN control, where we can optimize a lot of features over both physical and virtual infrastructure. I see lots of reasons why you would want to use Trellis as opposed to just traditional networking, even with bare metals, just instead of going to someone like Cumulus and SnapRoute. Because Trellis is designed for service provider use cases, many different kinds of traffic that all the fabric has to handle, some features that you can optimize, like I said, the virtual routing feature, newer features that you can actually change the data plane to include with this programmable data planes that are coming to the industry right now, and a business reason for some service providers who really care about having that ownership and full customizability that you can truly get with open source licenses. And so finally, one thing to remember about the roadmap is that Trellis has a different roadmap from CORD. Trellis has a number more features than CORD today, and those features will slowly move into CORD. But CORD is this integration project of a number of sub-projects, and those sub-projects are at different levels of progress. So CORD takes those and makes one integrated whole, but that also means that if Trellis supports V6, but other pieces in CORD, other projects in CORD are not V6 ready, that means you won't get them in CORD, but you will get them here. Okay, so a big thank you to all the people who work and contribute and try Trellis. We have a number of partners, and that's the end of my talk. I'm right at the 45 mark. So unfortunately, no time for questions because I do want everyone to take a break. But please do come back at 11 o'clock, where we will have Joe and Ashok from Broadcom telling you more about OFTP and all the wonderful things that we have done together, followed by EdgeCore, Jeff Catlin from EdgeCore, who will tell you about their bare metal hardware. Thank you.